Recording has started.
So for the first one here, we were told M is directly proportional to D. That's the same as saying M varies directly with D. So M equals K times D. Our next piece of information, when D is 8, M is 32. So we put 32 into that for M. Then we put 8 in for D. Now we can solve for that constant, K. When we divide both sides by 8, we get that 4 equals K. So the constant is K. So we can further define this relationship we had by putting that constant in there. It's not just M equals K times D, it's M equals 4 times D. And then we're asked, find M when D is 5. Well, we're just going to put 5 in there for D. 4 times 5, M would be 20. Number 2, P is inversely proportional to F. So P is inversely related or varies inversely with F. So P is equal to K divided by F. When F is 12, P is 3. So we put 3 in for P, 12 in for F, and then we solve for F. Here we're going to multiply by 12 to get F by itself. To get 36 equals, or solve for K, I should say. We multiply by 12 to get K by itself. So 36 equals K. So now we can, again, further define this relationship by putting K into it. P is equal to 36 divided by F. And then we're asked, find P when F is 6. So we put 6 in there for F. 36 divided by 6 is actually 6. So when F is 6, P is also 6. So that was the variation from yesterday. And as we mentioned, in engineering and science, there's a lot of relationships where we know they're inversely related or directly related. You can do a lot of calculation and work just by knowing that and being familiar with these relationships and this basic format of the formula, where then you can look at information that you already know and actually create the formula from it. So today we're going a little bit different direction. We're going to be coming back to the ratio and proportion in another couple hours of class, but we've got to define some basic geometry principles first. We did some basic geometry back in Unit 2. We did some areas and volumes. And we mentioned that everything in geometry comes from that feature right there, a point. We used that point before to make a line segment, and then that to make rectangles, to make areas and volumes and everything from there. Well, today what we're going to do is we're going to take that point, and we're just going to move it in a single direction and keep going. And what we form when we do that is called a ray. An array is defined by two properties. Actually, let me move this over here so I got room to write. There's two defining characteristics of array. It's the location of the starting point, which we could either have some sort of a coordinate grid, or we can just say our starting point is the center of any grid we would have. And that's usually what we do, is just define that starting point to be the center of any location grid that we would use. And then there's a direction. The direction, if we're looking at that grid, we define the right, or if you're looking like at a map, it would be the east direction is 0 degrees. And then we go around it counterclockwise. This would be 90 degrees, 180 degrees, 270 degrees, and then 360 degrees would actually be back at 0. The reason they did this is because back in the day, navigation was important. Many people, well, only a small portion of the population was educated, formally educated, and those that were formally educated typically had access to boats and spent time on the water, so navigation was a big deal. So the people that were educated were familiar with navigation. And this this grid system is how the directional navigation works as well. So we don't have the means here to measure that direction exactly, but let's say that that is going at 24 degrees is the direction of that ray. So that ray is defined as having this starting point and going in a direction of 24 degrees from 0. Now, if we have a ray like that, let's say that is going at 24 degrees from 0 still. If I go back to that same starting point, right back here, center of my grid, and I move that point now in a second direction, but a different direction, I might move it like this. So as the same starting point as that first ray, let's say this direction here is 71 degrees. Those two rays with the same starting point form an angle. The size of the angle is equal to the difference in direction. So going back to this one, this does form an angle. The difference in direction is going to be 71 degrees minus 24 degrees, which is going to give us 47 degrees. So the angle here formed between those two rays is 47 degrees. It's the difference in their direction. That is the formal definition of the size of an angle, the degrees of an angle. We've seen them all our lives, well, not all our lives, but since probably about 6th or 7th grade. We've seen the angles, 30 degrees, whatever, from 90 degrees. Their actual definition comes from that navigational grid. Now, through the years, navigation became less a part of everyday culture, or at least everyday educated culture, and a larger portion of the population now is formally educated, so it makes sense that not all of them would have that navigational need. So they've adjusted the definition of degrees and measuring an angle a little bit. What they've done is they've gone off of standards. So let's say that we take a point and we move in this single direction. Now we go back to that point and we turn all the way around and we move again, so it's actually in the same direction. How far we have turned here is a complete turn, which is 360 degrees. That is a complete revolution. In other words, we've turned all the way around. We might have an original direction here. And from that we turn so we're facing the opposite direction and we go. This is still an angle because we do still have that starting point there. Even though it really looks a lot like just a line, which it also is. But it would be 180 degrees because it is a half of a revolution. And half times 360, or half of 360 degrees, is 180 degrees. Likewise, let's get back here. We might have where we start off in a given direction, and from there we turn immediately to our left, and we go in that direction. This would often be marked with a square in the corner here, indicating that's a square corner, or 90 degrees, because this is 1/4 of a revolution. And 1/4 times 360 is 90 degrees. So we define the degrees of the angle by the fraction of a complete revolution that it turns. In fact, the opposite is true as well. If I have an angle here that is listed as 36, well, what the heck, 36 degrees. What that is saying is that it's 36 3/60ths of a revolution. If I wanted to reduce that fraction, both of those actually divide by 36, that is 1/10 of a revolution. Well, there are some special angles, and we've already seen two of them. But we want to talk about some relationships before we get back to those special angles. And that is something called adjacent angles. So, adjacent angles share that starting point, which is called a vertex, and one side. So let's create an angle here. So there's the two sides of my angle. The rays are the sides of the angle. This point here, that common starting point, is called a vertex. Well, if I create a second angle that has sides like that, has the same vertex, those two angles are adjacent angles. What is important or special about adjacent angles is that they're additive. What that means, if I know that this angle here is 41 degrees, and I know that this angle here is 78 degrees, then I can find this whole big angle by adding those angles. 78 plus 41, or 41 plus 78, however you want to do it, is 119 degrees. So that bigger angle is 119 degrees. Now, being able to add angles implies that we're also able to subtract angles. So if I have this initial angle, like that, and then I have a second angle, sharing a side and the vertex, if I know that this angle here is 29 degrees, and that this one here is, oops, that's not what I wanted. And let's say that this bigger angle is what I'm looking at here. If I know that that bigger angle is 73 degrees, then I can find this smaller angle, because I know if I called that angle x, these two angles, x plus 29, has to add up to the 73. To solve that equation, I have to subtract the 29. X equals 44 degrees. Because of that ability to create and solve equations, like I said, anything that we know is additive, that can be added up to find a total, can also be subtracted. If we have the total, we can subtract back to get one of the pieces. If I have two adjacent angles like this that form a right angle, they're actually what the formal term for them, which this textbook doesn't use and you won't be tested on, called a perpendicular pair. They add up to 90 degrees, or they make a perpendicular. So if I knew that this angle here was 38 degrees, this angle here would have to be 90 minus 38, or 52 degrees. Well, they're only a perpendicular pair if they're adjacent like this. But any two angles, if this one is 18 degrees, and this one is 72 degrees, those two angles still add up to 90 degrees. So like I said, the perpendicular pair only applies if they're actually adjacent and come together to make that right angle. These two are what are said to be complementary. They still add up to 90. Or a right angle. They're just not put together right now to make that right angle. They're not necessarily adjacent. These are still complementary. All perpendicular pairs are complementary. It's a special case of complementary. But in general, complementary angles do not have to be adjacent. Like I said, that term perpendicular pair is not something we're going to be tested on in this class, but I wanted to throw it out there as that special case. We could have two adjacent angles, excuse me, that create a straight line. This is called a linear pair. Makes sense. Perpendicular pair makes a perpendicular or a right angle. Linear pair makes a line. We know they add up to 180 degrees. So if I know that this is 46 degrees, this angle here can be found by doing 180 degrees minus 46 to get 134 degrees. Again, along the lines of that linear pair, the perpendicular pair and complementary angles, linear pairs, it's only a linear pair if they're actually adjacent and coming together to form that straight line. But I can have two angles. Let's say this is 94 degrees. And this is 86 degrees. Two angles that add up to 180 degrees are what we define as supplementary. Now we have those two words, complementary and supplementary. If you're anything like me, when I first learned those terms, I could remember the words, but I couldn't remember which one was which. And so the way I remember it is, you'll get complements when you are right. So complementary angles form a right angle. Kind of a silly little thing, but that was the only way I could remember those when I was young. Well, we have another special relationship. We look at intersecting lines. Or just pairs of lines in general, but here these two lines intersect. If I know one angle of these intersecting lines, let's say I know that this here is 43 degrees. I then know this angle here because this is a line. Those two angles are a linear pair. They form a straight line. In other words, they're supplementary. So this up here will have to be 180 minus 43, or 137 degrees. Now I also know this angle over here because this is a line. Those two angles come together to make a straight line, the 137 and this one, the one that we're looking for. They're a linear pair, which means they are also supplementary. So this angle over here is 180 minus 137. or 43 degrees. And finally, we would know this angle down here, because this is still a line, those two angles form a linear pair. So that angle would be 180 minus 43, which we've already subtracted to get 137. When two lines intersect, they actually form four angles, but those angles come in pairs. Those two angles are the same, and those two angles are the same. Those angles that are the same are called vertical angles. And they are on opposite sides of intersecting lines, and they have to be equal. So every time two lines intersect, they form two pairs of those vertical angles. When lines intersect, the pairs of angles that are formed are either equal, like the 43 and 43, or the 137 and 137, or they're supplementary. Like the 43 and 137. This, by the way, is what is referred to as oblique intersecting lines. Now, in two dimensions, all oblique pairs intersect. In three dimensions, like if this is a line, if you think of this arm as a line and this arm as a line, they don't intersect, but they're still oblique. And we'll further define oblique here over the next few minutes. We can have a special relationship between two lines called perpendicular. We mentioned the perpendicular pair earlier. Perpendicular lines are intersecting lines that intersect at a right angle. Now, because of what we just saw in that last example, we know that angle's 90 degrees. So this angle over here is its vertical angle, the opposite side of the intersecting lines. That's also 90 degrees. Well, this angle here has to be a supplement. Well, 180 minus 90 is 90 degrees. This is vertical to that one. It's also 90 degrees. When two lines intersect, to be perpendicular, or if two lines intersect to make one right angle, all four of the angles formed have to be right angles. They all have to be 90 degrees. Parallel lines. Now, one of the definitions that many of us have had of parallel lines is that parallel lines never intersect. That's not in two dimensions, that's adequate. But in three dimensions, it's not adequate. Again, this line and this line, they never intersect, but they're definitely not parallel. Parallel lines, the technical definition, are two lines that are always, I guess I didn't need the two in there, any set of lines that are always the same distance apart. Technical and mathematical terms, they call it everywhere equidistant. That just means they're always the same distance apart. But let's talk first about measuring distance. We'll start with a line and a point. If I want to measure the distance from that point to the line, that distance is always measured at a perpendicular to the line. So if I have two lines and I want to measure the distance between those lines, that one was crooked. That's a little bit better. I pick a point on one line and I make a segment that's perpendicular to the other line. That's the distance. I could pick any other point on that line and draw perpendicular to the other line. That should just be the same distance if they are parallel. Or I could pick a point on the other line and measure its distance to the one that we were picking points on before. That distance should be the same if they're parallel. So that's parallel lines. They're everywhere equidistant. They're always the same distance apart. Well, we're going to look here for a second at something called a transversal. A transversal is a line that cuts across at least two other lines. Now, it doesn't have to be parallel lines. Those lines are not parallel. This is still a transversal. Cuts across two other lines. But it's more interesting when that transversal cuts across a pair of lines that are parallel, like these two. Now, if I give you one angle here, if I tell you that this angle here is 71 degrees, I know all the angles around this intersection. I know this one's 71 degrees. This one up here is the supplement. 180 minus 71 is 109 degrees. This one down here then is also 109 degrees. But what about this intersection down here? Well, let's take this line here. Let's imagine moving it. Gotta use my mouse, I guess, to make that work. Up to the other line. We see that it lays exactly on top of that other line, and it forms all the same angles. So what that's telling me is this angle here is the 71 degrees. This angle here is also the 71 degrees. This angle here is the 109. This angle here is the 109 degrees. When a transversal cuts a parallel line, if this were a formal geometry class, there's all sorts of definitions that we would come up with. Don't write these down. You're not going to ever be tested on them. You're never going to have to remember them. But any angle that is formed between the parallel lines is said to be interior, because it's on the inside, between the parallel lines. Any angle formed outside is said to be exterior, because it's outside of those parallel lines. So if we have a transversal cutting across here, these four angles are exterior angles. These four angles are interior angles. Now, corresponding angles are on the same side of the line. So this angle and this angle are corresponding. They're also equal. But I could have corresponding interior angles. Well, that would be this one and this one are corresponding, but they're also both interior. Corresponding exterior angles, of course, would be the other ones on the outside. Alternate angles are on opposite sides of the transversal. Well, again, we don't need those terms, but at least if this is a formal geometry class, you'd have a bunch of alternate interior angles are equal, alternate exterior angles are equal, corresponding interior angles are supplementary, just corresponding angles are equal, corresponding exterior angles, I mean, you have all sorts of terms to deal with. We're not going to deal with those. For us, as you can see here, that angle, that angle, that angle, and that angle are all equal. And this one, this one, this one, and this one are equal to each other. And this one is supplementary to that one. So just like with our two intersecting lines, all angles formed are either equal or supplementary. So from those relationships, then, if we know one angle, we can find the other 7. One of the most useful geometric shapes that we have is the triangle. Now, you might not realize it, but triangles are everywhere around us. You might look around and see rectangles everywhere. The footprint of a house, the wall of a house looks like a rectangle. But there's actually a lot of triangles in there. A rectangle, anything that's structural, by the way, is triangles. A rectangle is not structurally sound. If I just make a rectangle, if I push on it hard enough here, it's going to, we call it racking. I used to work as a structural engineer, so that's a term I was very familiar with. It's called racking. If you push on a rectangle hard enough, it will squish or shift like that. It'll rack. A triangle, however, can't do that. You can push here as hard as you want to. It will not shift unless one of the pieces actually breaks. This here is just the nails bending or whatever and things shifting. So anything that's structural is made of triangles. If you look at the roof of a house, it's a triangle. In fact, within that triangle, there's usually smaller triangles put in there to add even additional structure to it. A wall of a house looks like a rectangle from the outside, but when you're building a wall, once you build the wall and set it up, you're going to take another board and put across it like this and nail it. And you'll notice that forms triangles, actually mini triangles. And those triangles hold that wall to keep it from racking like that. Otherwise, yeah, that wall will flop back and forth. It'll tilt if you don't put that extra piece on there. Now, in practice, once that wall is up and we start to work on it, you put sheeting on the sides. Well, that sheeting attaches it to it. But even that sheeting is forming triangles, because let's say you put a sheet of plywood on there, you have a nail pattern on that sheet of plywood. That nail pattern is forming those triangles to hold it in shape. So the triangles are a very important shape all around us. A triangle has interior angles, just like parallel lines have interior angles. Well, if I look at actually the exterior angles of a triangle, if I'm going in this direction here, I make a turn. I'm going to call this angle, actually I'm going to call it angle D. So I turn, so I'm heading now this direction. I get here, I turn here. I'm going to call that angle F, so that I'm heading in this direction. I get here and I turn. I call that angle E, so that I'm heading in this direction. Well, angle D plus E plus F add up to 360 degrees. It's a full turn. I started going in this direction. I came all the way back around, so I'm going back in that direction. So they're 180 degrees. Now I'm going to call the interior angles of this triangle A, B, and C. What I know here is that angle A plus angle D is a linear pair. It adds up to 180. B plus F is also 180. And C plus E is also a linear pair. That's also 180. Well, 180, if I add all 6 of those together, 180 plus 180 plus 180 is 540 degrees. But I only want the interior angles. I only want A, B, and C. So what I am going to do, now we saw in the last unit when we solve an equation, we can subtract the same thing from both sides of an equation and it's still the same. It doesn't change the value. Well, here I'm going to subtract 360 degrees from the right side. That gives me 180 degrees. On the left side, I'm going to subtract 360 degrees, but I'm going to do it in the form of angles D, E, and F, because I know those add up to 360. So I'll subtract angle D, subtract angle E, and subtract angle F. Those angles are gone. We're left with A, B, and C. And this is always true. No matter what triangle I drew, this would be true. The interior angles of a triangle add up to 180 degrees. It's referred to as the angle sum for a triangle. So if I know two angles of a triangle, if I know that this angle here is 26 degrees, and let's say I know this one here is 61 degrees, I can find this other angle because I'm writing an equation. X plus 26 plus 61 has to add up to 180. I can combine the 26 and 61 to make 87. So x plus 87 equals 180. And I subtract 87. X equals 93 degrees. Now, I didn't have to write out the formal equation. I could have just taken 180 degrees, subtract 61, and subtract 26, get the 93 degrees. But I wanted to show you that angle sum relationship there. Okay, with that, I have rambled on long enough for the day. Homework for you. Is on page 403. Exercise 12.1, 1 through 35, the odds. Looking at those angle relationships and the triangles. So we have about 8 minutes left. You're welcome to get started on that if you would like. I will be here to answer